Electric flux homework problem 2. We get the cylindrical surface of rho equals to 8 centimeters containing the surface charge density of rho s equals to 5 times E at minus 20 C in absolute value nanocoulombs per square meter. We're asked what's the total amount of charge present in the surface and how much flux leaves the surface and the rho equals to 8 centimeters. And when we get a C distance of 1 centimeter to 5 centimeters and the value of phi, that means the one that goes all the way around, goes from 30 degrees to 90 degrees. So one of the main things to do with this kind of problems is to identify what's the geometry we're working with. In here, it's very clear. We're working with a cylindrical surface. Two things to note. We're not saying what's the orientation of the cylindrical surface, and we're not saying what's going to be the length of the cylindrical surface. However, if we look closely at the charge distribution, we will see that it depends on C. So we can suppose that the cylindrical surface actually will look something like this. I'm going to exaggerate it, so it will be like a circle that's kind of going like that. So the cylinder would actually look like this. A cylinder center at the z-axis. C, X, and Y. Now, to make it more appealing, let's just say that it goes from one side to the other, up and down along the z-axis. That means it kind of goes like that. So our cylinder would actually look something like this. We get a cylinder that goes up and down from the center to center. It has a total length that we don't know. Total length that we don't know. That means we can say that it goes up a certain length and it goes down minus a certain length. As we know, it can go to minus infinite going down to plus infinite going up. We're not sure. We only know that's being located like that. Then we're saying that there is going to be a surface density of charge that's described like this. 5 times E at minus 20 absolute value C nanocoulombs per square meters. That means that we will have a surface charge in the surface that's surrounding the cylinder or the outer like cured surface of the cylinder. Here we have the charge. Here we get the surface charge. If we want to know what's going to be the total charge of this, we should multiply it by an amount of area to eliminate these square meters. Or we apply an integration. So total charge is going to be a surface integration of rho s differential surface. And as we recall, the differential surface for a cylinder is going to be rho d phi dc. Now, since we work with a surface that has a specific radius will be a fixed value. So no need to integrate about the radius. That way we're actually calculating only the one surface around it. We can start replacing q equals to the double integral of rho s. And my rho s is going to be 5e at minus 20 c times surface differential element, which is going to be rho d phi dc. We're working with the first part, total charge contained on it, right? Right. Now, the integral is going to be about L or C, and it's going to be about phi. Phi is the angle describing the turn. That means goes all the way around. So phi will be from 0 to 2 pi. Since we're working with the all on the full turn, that means 0 to pi. And C, it's going to go from minus L to L. So minus L to L. We can start substituting some values. For example, the problem says that we're working in a specific row of 8 centimeters. That means this row becomes 8 centimeters. And 8 centimeters is 0.08 meters. 5 and 0.08 are going to be constant. That means they can be taken out of the equation. So Q equals 5 times 0.08 integration from minus L to L, integration from 0 on 2 pi of E at minus 20, and the absolute value of C, we can express it as positive C, always positive C. If we're working always with positive C, and we know that here we got a symmetric integration, this thing can be replaced actually by 2 times the integration from 0 to L, making everything easier. From here, we're about to start. One more thing. We have the integration from 0 to 2 pi of d phi. However, we don't have any phi variable here. If we don't have any phi variable here, the integration of this is going to deliver phi evaluated from 0 on 2. That means we can reduce q equals to 5 times 0.08 times 2 times phi evaluated from 0 on 2 pi, and now the integration from 0 to L of e at minus 20 c dc. This one will become 2 pi, so we can reduce everything. And reduce everything to a simple integration. Q equals to 5 times 0.08 times 2 times 2 pi times the integration of e at minus 0c. That integration has to be e at minus 20c over minus 20 evaluated from 0 to L. That means we will have Q equals to 5 times 2 times 2. That's going to be 20. Oh, this is 20. That's going to be 20. 20 times 0.08 pi times the evaluation of E when we got minus 20L minus the negative over 20 minus E at 0 over minus 20. Now, this minus with this minus, they can, sorry, this 20 with this 20, they can go away, and we will get only the exponential part. To reduce the system, we can write it down to something similar to this. Q equals 0.08 pi times this minus and this minus become positive, and E at 0 is going to be 1 minus E at minus 30L, like that. That would be the total charge. Now, if we want to get a number, we will just give a number to L. What if we analyze in the case that we get an infinitely long cylinder? That means L equals to infinite. If we do that, all this section becomes 0. In that case, we will have that the charge is going to be only 0.08 pi nanocoulombs total. Remember this, if L equals to infinite. This is what happens. And the final charge is going to be 0.08 pi nanocoulombs.